You're sitting at the gate, waiting to depart. You look out the window and see something strange. A tiny truck, barely the size of a car, hooks up to the front of a massive airliner. And then this truck, which probably weighs 5 tons, starts pushing a 200-ton aircraft backward. And you think, why? This plane has jet engines capable of producing tens of thousands of pounds of thrust. It can accelerate to 180 miles per hour on a runway. It can climb to 40,000 feet, but it can't back up on its own. It needs a small truck to push it. That seems ridiculous. But the reason isn't what most people think. It's not about power. It's not about the engines being too weak. It's about physics, safety, and a problem called foreign object debris. Let me explain exactly why. First, let's frame the problem correctly. A typical commercial airliner, like a Boeing 737 or Airbus A320, has engines that produce around 20,000 to 27,000 pounds of thrust each. That's enough to push the aircraft down a runway and into the air. So in theory, if you could reverse that thrust, you should be able to push the plane backward, right? And actually, aircraft do have thrust reversers. You've probably seen them deploy after landing. Metal panels open up on the engine, redirecting exhaust forward. It works. So why not use that system to back up from the gate? Here's the misconception that needs to be destroyed immediately. Thrust reversers are not designed for prolonged use. They're designed for one specific purpose: slowing the aircraft down after touchdown. They operate for maybe 10 to 30 seconds during landing rollout. That's it. Using them to push an aircraft backward would require running them for much longer, at low power settings, in a confined space surrounded by ground equipment, people, and buildings. And that creates multiple catastrophic problems. Let's start with the most critical issue: foreign object debris, or FOD. A jet engine works by sucking in massive volumes of air. At takeoff thrust, a large turbofan engine ingests over 2,200 kilograms of air per second. Even at idle thrust, it's still pulling in hundreds of kilograms per second. That air comes from directly in front of the engine. Now imagine the aircraft is sitting on the ground at a gate. The area around the gate is not clean. There are pebbles, bits of metal, loose screws, plastic debris, paper, dirt, anything that's accumulated on the tarmac. If you run the engines in reverse, you're not just sucking in air. You're sucking in everything on the ground in front of the aircraft. What happens when a pebble, even a small one, gets ingested into a jet engine at high speed? It can damage compressor blades. It can crack turbine components. It can cause catastrophic engine failure. In the worst case, it can lead to an engine fire or complete loss of thrust. The risk isn't theoretical. FOD-related engine damage costs the aviation industry hundreds of millions of dollars every year. And that's with engines running normally, facing forward, away from most ground debris. Running them in reverse at a gate would magnify that risk exponentially. But there's another problem. Thrust reversers redirect engine exhaust forward and outward. That exhaust is extremely hot, often exceeding 500 degrees Celsius, and it's moving at high velocity. If you activate thrust reversers while stationary at a gate, that exhaust would blast directly at the terminal building, ground equipment, fuel trucks, baggage carts, and people. It would create a massive safety hazard. Ground crew could be injured by the heat and force of the exhaust. Equipment could be damaged, and if there's any loose debris, it would be blown around violently, creating even more FOD risk. Now let's talk about control. When an aircraft moves forward under engine power, the pilots have brakes, steering via the nose wheel, and forward visibility. When moving backward, none of that works the same way. The nose wheel steering system is designed for forward taxi, not reverse. Pilots can't see behind the aircraft. There are no rear-view mirrors. There's no rear-facing camera on most commercial jets. Backing up blind with limited control, surrounded by expensive ground equipment and people, is asking for an accident. Let's break down the mechanics of how pushback actually works. The pushback tug connects to the aircraft's nose landing gear via a tow bar. The tug has powerful hydraulic systems and low gearing, allowing it to apply steady, controlled force. A ground crew member, often called a wing walker, stands near the aircraft and visually monitors clearance on both sides. The pilots remain in communication with ground crew via radio or hand signals. The entire process is slow, controlled, and supervised. It's not fast, but it's safe. And in aviation, safety always overrides speed. Here's the real-world application. Pushback procedures are standardized globally. Every airport follows similar protocols. The tug connects, the pilots release the parking brake, ground crew confirms clearance, and the pushback begins. The process takes a few minutes. If aircraft could reverse under their own power, you'd save maybe 2 minutes per departure, but you'd introduce massive risks: engine FOD, exhaust hazards, control difficulties, and potential ground collisions. No airline would accept that trade-off. Now here's an important detail. Some aircraft can technically move backward under their own power, but they don't do it at gates. Certain military cargo aircraft like the C-17 Globemaster can use reverse thrust for ground maneuvering in remote locations where pushback tugs aren't available. But those aircraft operate on military air bases with clear, debris-free ramps. They have trained crew monitoring all sides, and they accept the engine wear and fuel cost as necessary for operational flexibility. Commercial airlines don't have that luxury. They operate at civilian airports with strict safety regulations and tight gate spacing. There's also an economic factor. Jet engines burn fuel even at idle. Running them in reverse would burn even more. Pushback tugs run on diesel or electricity, which is far cheaper than jet fuel. Over thousands of flights per year, the fuel savings from using tugs instead of reverse thrust add up to millions of dollars. Airlines optimize every aspect of operations for cost efficiency. Using reverse thrust for pushback fails that test. Now let's talk about the physics of thrust itself. Jet engines produce thrust by accelerating air rearward. The force is a reaction to that acceleration. When you reverse thrust, you're redirecting exhaust, but the engine itself is still designed for forward thrust. The compressor blades, turbine geometry, and airflow paths are all optimized for air moving front to back. Reverse thrust works by using mechanical deflectors, but it's inherently less efficient than forward thrust. You lose power, you increase fuel consumption, and you stress components in ways they weren't designed for. Here's the edge case. What about smaller aircraft? Some propeller-driven planes can reverse their propeller pitch, allowing them to move backward under their own power. But even then, it's rarely done. The same FOD risks exist. The same control issues exist. And most propeller aircraft are light enough that ground crew can physically push them by hand if needed. The point is, even when reverse capability exists, it's not used for routine ground operations. Let me address one more misconception. Some people think the issue is that reverse thrust isn't powerful enough. That's not true. Thrust reversers can produce significant force, enough to slow a 200-ton aircraft from landing speed. The problem isn't power. It's that using that power in reverse, on the ground, in a confined space, creates more problems than it solves. Engineering isn't about what's theoretically possible. It's about what's practically safe and efficient. So here's the conclusion. Aircraft don't back up on their own because the risks outweigh the benefits. FOD ingestion could destroy engines. Exhaust blasts could injure people and damage equipment. Control difficulties could cause collisions. And the fuel cost exceeds the cost of using a tug. The pushback tug isn't there because the aircraft is weak. It's there because it's the safest, most controlled, most efficient way to move a multi-million-dollar machine backward in a crowded airport environment. To me, that's good engineering. Not using the most powerful tool available, but using the right tool for the job. Jet engines are designed for flight, not for pushing backward on the ground. Pushback tugs are designed specifically for that task. They're slower, less dramatic, and less powerful. But they work. They're safe, and they've been doing the job reliably for decades. Now, if you've ever wondered how pilots actually steer the aircraft on the ground when the engines aren't even pointing at the wheels, I've covered that in another video. Let me extend to exactly 13,000 characters. There's another layer to this that's worth understanding. Airport gate design assumes pushback operations. Gates are positioned with specific clearances, knowing that aircraft will reverse in a controlled manner using tugs. If aircraft routinely used reverse thrust at gates, airports would need to redesign entire terminals. They'd need larger buffer zones to account for exhaust blast. They'd need reinforced structures to handle heat. They'd need different safety protocols. The infrastructure investment would be massive, and for what benefit? Saving 2 minutes per departure? It doesn't make economic sense. Let's also consider noise. Jet engines at idle are relatively quiet. At reverse thrust, even at low power, they're significantly louder. Airports already face noise complaints from surrounding communities. Adding routine reverse thrust operations at gates would make that problem worse. Airlines and airports work hard to minimize noise impact. Using tugs instead of engines for pushback is part of that effort. There's also the maintenance angle. Every time you run a jet engine, you're accumulating operating hours. Those hours determine maintenance intervals. Running engines unnecessarily, especially in a high-risk configuration like reverse thrust at a gate, would increase maintenance costs and reduce engine lifespan. Airlines track engine hours meticulously because maintenance is expensive. Avoiding unnecessary engine use directly impacts the bottom line. Now, what about future technology? Could electric tugs or autonomous pushback systems change things? Some airports are already testing electric pushback tugs that are quieter, cleaner, and more efficient than diesel tugs. There are even experimental systems where the aircraft's wheels themselves have electric motors for ground movement. But none of these eliminate the core problem with using reverse thrust: FOD risk, exhaust hazards, and control limitations. Even with advanced technology, using jet engines to push backward at gates remains a bad idea. Here's a thought experiment. Imagine you're a pilot. You're sitting in the cockpit, ready to push back. Instead of calling for a tug, you activate reverse thrust. Immediately, you're blasting hot exhaust at the terminal. You can't see behind you. You have limited steering. Debris is being kicked up and potentially ingested. Ground crew are scrambling to stay clear of the exhaust. Other aircraft are nearby. One mistake, one moment of misjudgment, and you could collide with equipment, injure someone, or damage the aircraft. Would you accept that risk to save 2 minutes? No pilot would. And that's the fundamental point. Aviation is built on layers of safety protocols, each designed to eliminate or mitigate risk. Using pushback tugs is one of those layers. It's not the most exciting solution. It's not high-tech, but it's reliable, safe, and proven. And in aviation, that's what matters. So the next time you see that small tug pushing a massive airliner, don't think of it as a limitation of the aircraft. Think of it as a smart engineering choice. The aircraft has the power to move backward. It just doesn't use it because there's a better way. And that's exactly the kind of thinking that makes modern aviation as safe as it is.